Okay, section 5.3. The last show you know exemplar here is how to subtract polynomials. And in order for us to have to be able to understand modeling of subtraction, we have to go back to grade 7 for just a second. In grade 7, you learned that when you had -2 take away a +3, right? You learned how to represent that with integer chips. And what you did was something like this. You took, oh, that's not what you take, hang on. You learned that you could take a space and you could put the first term of -2 in, okay? So -2, we're going to represent with 2 negatives. And if we interpret that, from -2, we have to remove 3 positives. And you were like, well, from a modeling perspective, I can't remove positives from a negative. However, what is the value of that right there? 0. So if we take this, in grade 7 you learned that if we infinite clone it, I can bring as many of these as I want in here. And what is the value inside that box, the total value inside that box? It's still -2. And even if I put one more in, it still has a total value of -2, agreed? But the reason why we put those 0 pairs is because now we have the ability pictorially to be able to do what we're asked to do. It says -2, take away +3. So there's -2, take away +3, and what do we get for an answer? -5. So we learned that from a modeling perspective with integers in grade 7, we learned that you model it, you understand why taking 2 negatives and subtracting positivity from something negative makes it more negative. If you subtract positivity from something that's negative, you make it more negative, and that's the pictorial representation. We then also learned that you can get the same answer. You can get the same answer by changing it, by keeping the first term, changing the subtraction to addition, and using the opposite of the second term. And 2 negatives combined with 3 negatives is 5 negatives, right? So that was your grade 7, Chloe, your outcomes for integers. The first one was how to model it, and the second one was realizing that the keep, flip, change idea to subtraction of integers works. Now, why am I showing you this? Well, that same principle happens to work with algebra as well, with polynomials. So if I erase this, so now that we have that, let's look and apply that exact same thing with this question here. 2x minus 3 minus -x plus 2. So again, we're going to start with a space, and into that space, I'm going to put my first term. So we're going to represent 2x minus 3 with an x and an x and a minus 3. Now, according to what we're doing here, this term, we're going to remove from it a -x and a positive 2. Do I have a -x or a positive 2 in there? No, I don't have either one of them. But remember, algebraically, this one and this one make what number? So just like the other one, if I bring that in, does that affect 2x minus 3? No, it still is a value of 2x minus 3. But what it allows me to do, I can now subtract a -x. Take that -x and subtract it. You agree? But now it affects the answer. But then if I have to take away a positive 2, I'm now going to take a 0, bring that in. I'm going to take another 0, bring that in. I haven't changed the value, but now I can remove a positive 2. Does everyone see that? So I never changed the value because every time I brought something in to remove, if I needed to remove something that I didn't have, I brought in algebraic or integer 0 pairs to give me enough of whatever it is I needed to remove. And now when I look at what the answer is, what's left inside that box? We have 3x and minus 5. Agreed? And that's your answer. So this will equal 3x minus 5. Okay? That's how we model our solution. Now, how do you think we're going to do it on a test? What do you think the method we're going to use? Keeping in mind with integers, if you were given this question in grade 7, you probably didn't use modeling to get that answer, did you? What did you use? You always use keep flip change because you knew that it was going to get you the cap flap change. That's the one you use. You knew that that worked, so you would change it to this. And you get your answer -5. So let's apply that logic. Let's apply that logic to polynomials. Let's see if it works. We have 2x minus 3, take away -x plus 2. We are going to change this to 2x minus 3 plus what? No. What's the opposite of the first term? What's the opposite of -x? Positive x. What's the opposite of positive 2? Subtract 2. Do you guys see how those are going to work the same out? Just like integers, we're going to add the opposite. And now when we gather our like terms, a 2x is going to combine with an x to make what? 3x. If it comes out, where's my marker gone? There it is. If we combine a -3 with a -2, that's going to make -5. There's the same answer I just got. But instead of modeling it, and instead of adding those 0 pairs and yada, 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 I simply realized that that idea of keep, flip, change works so much better with polynomials just like it did with integers. Okay? Does that make sense? Danny, does that kind of make sense? Did you use keep, flip, change in grade 7? You did. So the same thing works here. So let's use that again then. Let's try that one more time. If we're going to combine like terms, I'm going to do the non-modeling part. I'm going to take this expression, 5x squared minus x plus 4, and I'm going to add the opposite of that trinomial. I'm going to use the opposite. Keep, flip, change, right? Changing it. So, CJ, what will the trinomial here become if I'm going to add the opposite? What's the opposite of this trinomial? -2x squared, positive 3x or plus 3x, plus 1. So these two should have the exact same answer, right? If we're using our integer logic, right? Adding the opposite should work. Now that we get that, my x squared terms, do I have any x squares over here? Yes, I do. I'm going to keep the x squared, and I'm going to combine the coefficients. What's a 5 coefficient and a -2 coefficient make? 3. My next one, I have a -1x and a positive 3x. I'm going to keep the x and combine the coefficients to make positive 2. There's a positive 3 and a -1. Yep. And finally, a positive 4 and a positive 1 are going to make a positive 5. Now, what I'd like you to do right now is the hardest part. I want you to try and model this subtraction question and see if you can get it. I'll start you off. I want you to start with a box. And in that box, we're going to draw 5x squareds. 1, 2, 3, 4, 5. 5x squareds, a -x, and a positive 4. Now what I want you to remove from this, I want you to remove that entire binomial and see if you can do it. And then I'll show you what the answer looks like. While we were on pause, 91 ice cream sandwiches, so they're a little off task right now. But here we go. So from this expression, which is right here, we're going to remove all of this. So can I remove 2x squared from this picture? The answer is yes, I can. So I'm going to circle 2x squareds and remove it. Okay, I didn't need to add anything to it. I had enough in there. I also have to remove -3x's. Do I have -3x's? I just have one. So here's the question. How many algebraic 0 pairs do I need to add to this box to make it work? 2 of them. So I'll make one like this. That's 0. I'll make another one like this. That's 0. And now I have enough to remove 3, 3 negative x's, or negative 3x's. And finally, can I remove a negative 1? No, I can't. There's no negative 1s there. I can add 1 0 pair, and now I have enough to remove a negative 1. And if we look at what we have left, oh, my highlighter's not working. We have 3x squareds, which is right here. We have 2x's, which is right there. And we have positive 5, which is right there. So we represented that whole same thing mathematically without using the model, or with just using modeling. Okay? Any questions?